Welcome to all. So in this session I am going to explain the experiment number 6 in integrated electronics lab, construction and verification of 4-bit ripple counter and Mod-10/Mod-12 ripple counter. So our aim is to design the 4-bit ripple counter and Mod-10 and also Mod-12 ripple counter. So in this experiment we need the following apparatus record. So we need for the JK flip-flop. So for that purpose I am going to use the IC7476. So it consists of 2 JK flip-flop. So for our 4-bit ripple counter we need for the 4 JK flip-flop. So we are going to use the 2 ICs and one more gate is NAND gate IC7400. So for this purpose I am going to the restrict the input counting of clock signals, so to Mod-10 and also Mod-12 from the 4-bit ripple counter and a digital trainer kit. So these are the requirements. So first of all, so counter is a register, so it is capable of counting the number of clock pulses arriving at its clock input. So it has two types, one is synchronous counter, another one is asynchronous counter. So synchronous counter, so we need to apply common clock pulse for all the flip-flops, so that is called synchronous counter. So asynchronous counter means, so we are going to apply so external clock pulse to the first JK flip-flop. The output of first JK flip-flop is given to the clock signal of next stage flip-flop. So in this case, so we are going to give the each successive flip-flop is clocked by Q or Q output of the previous stage output. So this is the working principle of counter. So now I am going to discuss the 4-bit ripple counter. So this is the pin diagram for IC7476. So it consists of 2 JK flip-flop. So pin number 1, clock 1. This is preset 2. That is preset number 1. It's a clear signal. So J1 in number 4. VCC is number 5. Clock 2 is going to apply number 6. Reset is pin number 7. Clear is pin number clear 2 is the pin number 8. So 16th pin is K1. 15th is the output Q1. 14th is the Q1 bar. 13 is the ground. 12th pin is gate 2. 11th pin is Q2. That is output of the second JK flip-flop. And the 10th pin is Q2 bar. So 9th is J2. So in this pin diagram, so this IC consists of 2 JK flip-flop. Okay, this is the logic diagram for 4-bit ripple counter. So in this case, I am going to design the 4-bit ripple counter using the JK flip-flop. So this is IC7476. This IC consists of these 2 JK flip-flop. This is first JK flip-flop. This is second JK flip-flop for the first IC7476. This is another JK flip-flop for this IC number 2. So for this purpose, I am going to use the 2 ICs. First one is 7476 IC and for third and fourth JK flip-flop. So it is another 7476 IC. So we need to give the high input for the pin numbers, so 4 and 16. So we need to short circuit the pin number 4, that is J1 and K1. So 4 and 6 is short circuited. In this connections we want to apply the high voltage signal, that is high signals. Similarly here 9 and 12 is the another JK flip-flop. In this purpose we want to give the high value. Similarly for the next IC, 4 and 6 for the high value input and 9 and 12 for the apply the high input signals. So next one is, so in this clock signal is applied the pin number 1. So in this case I am going to apply the external pulse, clock pulse to the first flip-flop only. So output of the first flip-flop is given to the input of the clock pulse of second JK flip-flop. That is 15 is the output of the first JK flip-flop. So it is given to the clock pulse for the second JK flip-flop, that is pin number 6. Similarly, second JK flip-flop output 11 is given to the clock of second IC JK flip-flop, that is third JK flip-flop pin number 1. So next output of this third JK flip-flop 15 is given to the fourth JK flip-flop as a clock pulse in pin number 6. So next is, so we want to apply the clear signal. So for the pin number 3, pin number 8 for the first JK flip-flop and second JK flip-flop. So third JK flip-flop also we want to apply the pin number 3 and pin number 8 for the clear. So finally we got the output in QA, QB, QC, QD. So output is taken for the QA is the first JK flip-flop output in the pin number 15. So second QB is the pin number 11, so output of the second JK flip-flop, and QC is the output of the third JK flip-flop pin number 15, and so in pin number 11, so QD is the output. So this is the logic diagram and connection diagram of a 4-bit Ripple counter. So this is a truth table. So our aim is to calculate the clock pulses. So if you apply the clock pulses 0 means, so it is split into 4 binary numbers. That is, for example, so clock signal you are considering in VCD format means, so this is output QA, QB, QC in the binary form. So if clock signal is 0 means all the values equal to 0. So this is a combination for 8, 4, 2, 1, 4. So 0 means, so all the values are 0. So total value is equal to 1. So if you apply the clock pulse 1, so QA is equal to 1. So value is, this is a busy number 1 means this is a binary number. Next, clock pulse 2 means, so it becomes 0, 1, 0, 0. So clock pulse 3 means, so 1, 1. So for example, QA's value is 1 means, 8AC is 1 means, this is 2 means 1 plus 2 is equal to 3. Similarly 4, so this is the 4 value, QC is equal to 1. So if you apply the clock pulse 5 means, so 1 plus 4, that is 5. 6 means, so 2 plus 4, 6. So 7 means 1 plus 2 plus 4, that is 7. So in this case we are going to apply the clock pulses. So our 4-bit Ripple counter automatically counts the clock signals based on the input clock pulses. This is the output of the binary value. So in this 4-bit Ripple counter, so up to 0 to 15 we are going to apply the clock pulses. So it will be counters the clock pulses as per the 16 combinations 0 to 15. So final value if you apply the 15th clock pulse means, so all the values are equal to 1. This is 1, 2, so 1 plus 2 plus 4 plus 8, so total value is equal to 15. Okay, this is the logic diagram for Mod-10 ripple counter. So Mod-10 ripple counter counts the clock pulses up to 0 to 10 value. So 4-bit ripple counter counts the values from 0 to 15. So but in this Mod-10 counter counts the clock pulses from 0 to 10. So after the applying the 10th clock pulse, so all the values have resetted, so that becomes 0, 0, 0, 0. So the remaining operation is similar to the 4-bit ripple counter. So this is the connection diagram. So except this part, so remaining connections are similar. So here we are using the additional 7400 NAND gate, so to limit the clock pulses count from 0 to 10. So because this is a Mod-10 counter, so this combinations stop the counting the clock pulses 0 to 10 only allows, except remaining values will be output is resetted, that is clock signal is resetted. So here, so output of QD is given to the input of NAND gate, one of the input, and output of QB is given to the input of another input for the NAND gate. So one input from the QD, one input from the QB. So output 3 is taken from this third point, that is given to the preset to the all the flip flops. So for this combination, so this ripple counter counts the clock pulses from 0 to 10. So this is the truth table. So if you apply the clock pulse 0 means all the binary numbers are 0. If you apply the 1 means, so this value is 1, total weightage is 1. So similarly 2 means 0, 1, 0, 0. 3 means 1, 1, 0, 1, that is 1, 1, 0, 0. 4 means 0, 0, 1, 0. 5 means 1, 0, 1. Total weightage is 5. So finally, so the clock pulses reaches the 10 means automatically it will be resetted, that is 0, all the values are 0. So this is the logic diagram for Mod-12 ripple counter. So this is almost similar to the Mod-10 ripple counter. So this Mod-12 ripple counter counts the clock pulses from 0 to 12. So here, so we are using the NAND gate. So one input is given from the clock pulse, that is output of the fourth JK flip flop, and second input of this NAND gate is given from the output of the, so third flip flop, that is a C. So QC and QD and QD is the input for the NAND gate. The output of this NAND gate is given to the all the preset value for the JK flip flop. Okay, for this above connections, the truth table is the clock counter counts the clock pulses from 0 to 12. For 12th clock pulse, so all the value will be reset, that is 0 0 0. So this operation is similar to the 4-bit triple counter. So it counts only 0 to 12 clock pulses at the clock pulse 12. So all the values is equal to 0. It takes memory. So this is the implementation of 4-bit triple counter in digital trainer kit. So this is the input port. This green and also the input port. This is output port. Is so we are going to use the two ICs. One is IC 7476 for the first two JK flip flop. So this is for the second IC for the JK flip flop 3 and 4. So as per the logic diagram, the connections are made. So this is a 16 pin IC. This is 16 pin IC. So we want to apply the VC signal for the fifth pin for both ICs and ground signal for the 13th pin. So high signal is one of the input. We want to give the high signal from the input port. Always apply the high signal to the all the JK flip flop pin number 4 and 16 and 9 and 12, and also second IC 4 and 16 and 9 and 12. So input is always high for this all the flip flops. Next is we want to apply the external clock pulse for the first JK flip flop. So this is the clock pulse. So if we apply this clock pulse to the first JK flip flop, so output of the each stage is given to the clock pulse for the next stage. So we are giving only clock pulse to the first JK flip flop. So automatically output of the respective stages given to the input of the upcoming stages. And a clear signal is given to the pin number 3, 8 for the first IC, similarly 3 and 8 for the second IC. Next preset signal is given to the pin number 2, 7 of first IC, similarly pin number 2 and 7 of second IC. So all the connections are made as per the given logic diagram. Okay, so this is the clock pulse. So now I am going to give the automatic clock pulses to the first flip flop, that is 14 and 16 is already short circuited. We are going to apply the clock pulses to the pin number 1. So output of this first and the second is given to the respective upcoming stages. So this is the clock signal. So automatically it varies from 0 to clock pulse 15. So this is the high value. So this is the high value. So as per the connections, we want to give the input to all the 4 flip flops. So this is the clock signal. So this is the reset the values. So this is the reset button. So now, so output is, that is QA, QB, QC is equal to 0 as per the truth table. So now I am going to give the clock pulses to the first flip flop. So it automatically counts. So I am resetting the flip given the clock pulse to the first flip flop. So this is output 1, 1 0, 1 0 0. This 4. This is 8, 9, 10, 11, 12, 1 to 15. So one more time I am going to explain the output. So I am resetting the button. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So after that it automatically will be 0. Again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Automatically it will be resetted. So as per the our concept, it is a 4-bit ripple counter. So 0 to 15 clock pulses will be applied. So 15th clock pulse, automatically all the values is resetted. Similarly for 4-bit, that is Mod-10 ripple counter. So our counter counts the clock pulses from 0 to 10. So if you apply the clock pulse 10, so all the values will be resetted. That is, output is QA, QB, QC value is equal to 0. Up to 0 to 9 it counts the clock pulses. So 10th clock pulses automatically it will be resetted like a 0. So similarly mod 12, so ripple counter, so it counts the clock pulses from 0 to 11 is the number. If you give the 12th clock pulse means automatically it will be resetted. So QA, QB, QC is equal to 0 like 0. So this is a implementation of 4-bit ripple counter, mod 10 counter and mod 12 counter. So from this implementation, so I verified the truth table for 4-bit ripple counter, mod 10 counter and mod 15 counter, mod 12 counter. Thank you.